our first speaker is Professor Yero. He will talk about K-metric, anti-dimension, and privacy in social networks. So let's welcome Professor Yero.
Thank you for the presentation of this last lecture of this course. It has been a pleasure for me. And we had today to go a little to this ceremony, so we began a little later, but it was also nice to see how the students here are getting their results at some point. Yeah. So today I will be speaking with something related with metric dimension, as I have been speaking till now, but today we will kind of switch to another direction, I would say. Yeah. First, I will tell some kind of story about how this came out. Well, as you remember, I was speaking till now about this metric dimension stuff, in which we have a graph and a set of vertices, which is a resolving set, which has the ability to identify all the vertices of the graph by a unique way. I mean, each moment one resolving set knows which one is which one. Yeah, it means that for everyone there is a unique vector of distances that identify this field. And then a few years ago, I remember I was, I have been working with that for long. And at some point I decided that I was thinking that why should we always consider the case in which that vertices are identified by someone? Why not go to consider that the vertices will be not identified? Yeah. So then I thought it is probably possible that I will consider a set of vertices such that for any two vertices outside, they will have the same distance to all the vertices of this set. Yeah. Oh, this is important. This is indeed possible, and this is the first idea I had, and this idea remained there. And I was speaking with my colleague about this, that we should consider this. And then this guy is a computer scientist, and he is also a specialist on privacy in social networks. And he was thinking a little about it. Well, I have to say, I have to be a little more honest. I know that here in Pakistan is in general not allowed to drink alcohol, but this day we were sitting in the bar and we were drinking some beers, me and this guy. And he was, okay, this idea seems not to be so specifically important. And after a few beers, then he came out with the idea which really was useful. What means that? He told me that we will, instead of considering a set of two vertices that they will have the same distance to this, we need to consider that for each vertex, there will be another vertices that they will have all the same distances to the set of vertices, which is not the same in it. I'm not considering pairs of vertices, but only one vertex. And for me, there should exist another ones, yeah, that they will all have the same distance to this set of vertices. Why this is interesting? Because imagine you have a network which represents something, yeah, people which are doing something, sharing something. And if this set has this property, and this set is controlled by some guy which is having bad intentions, this person cannot know exactly who I am, because I know that for each of these vertices, there are a group of people of I don't know, some value k, 2, 3, 4, 5, so that we are all the same. So we cannot be distinguished with probabilities smaller, larger than 1 over k, right? Yeah, if we are k and me, so I'm probability of that there are some people which are like me, yeah? And then this told me, this is the idea of what we can use really for something, and it should be indeed applied. It could be indeed applied to privacy in social networks. So then we thought, okay, this is what we decided that we will do, and then we will begin to study. And then this gave birth to this K metric anti-dimension. We call anti-dimension because it's not dimension, it's something like on the contrary. So it's not exactly related, but it comes from this first way. And then I recently realized that my previous idea, that one, in which any two vertices, for any two vertices, there exist, for any two vertices, take a set so that they will have the same distances to all the vertices. This was explored by other people recently in an article which appeared in the Bulletin of Malaysian Mathematical Sciences Society. And they are calling that equidistant metric dimension. So you see, if I will continue this other idea, I will also get something. Indeed, the article which they did is really interesting. I suggest you, if you are interested, to see this equidistant metric dimension. There is only one work on the topic, so you might consider it as a possible topic for research. Yeah, but this, what I am doing, is completely different from this equidistant. So I told you the story of how this was born. Work in this. Okay, now. So here I will speak first a little about some kind of privacy things which are not related, in order that we'll after better understand everything. So we have social networks and privacy. In general, this is a topic which is used by many people like sociologists, economists, and it's very useful for things like advertisement and things like that. So there are good studies on social networks and privacy. I mean, it's not only the bad part. Of course, all that things are then not free of cost, and we can then have some problems. And when we have a social network, well, first I should be clear that what social network is. I mean, social network is not Facebook, not Twitter. I mean, it's not this. Well, these are social networks, but not the social networks that we really consider. By social network, we mean data. Yeah. For instance, if you have hospital and all the users of this hospital, and for each of the users, you have some information. Yeah. The age, the, I don't know, sicknesses which they have, their treatments, and things like that. So these data are many times stored somehow in some place so that after scientists will work with them. But of course, this is not nice, because if I am, for instance, in this table, yeah, and my data are there, probably I will not be happy that someone will know that I have some treatment because of something. So the data should be studied, but without reference to the people exactly which are there. Yeah. But of course, if there is something that someone will want, probably will enter and dig a little there, will probably decide, find where I am, who I am. And maybe we will say, oh, this is the guy which is there. Yeah. Then they will know many information about me. So then it is used some kind of anonymizing processes to identify things that are potentially easily to discover. For instance, if there is a network in which I am the only one which is having some specified situation, yeah, and then they form a kind of graph with this, then I will be kind of isolated. So they will easily know that I'm me, because the only one which is that is me. So it's clear. So the idea is that then I will remove all the things in these anonymizing processes. And there are even some other processes, that is privacy preserving methods that are necessary to be used in order to be public, to make public the information. Yeah. So they are based in this concept called k-anonymity, which is known for some computer science things. And the idea is that in a database that you will be public, you will make public, the probability that you will be re-identified should be higher than 1 over k for some value k. Of course, as much as this probability it is, then you are in troubles. Yeah. So there are several anonymization methods that I will not enter in this. This is not my topic. But even so that you will use some anonymization methods, you have to know something that will measure how secure a network is. I mean, you can take a network, you can anonymize it, then you will get a new network that you make public, but there is no kind of measure that will say this social network has some measure of being there that you have some probability of being identified or not. Yeah, and this is what precisely we did. Yeah, we were trying to give a measure of how much secure is a social network against some kind of attacks. Of course, this is another thing. There are different kinds of attacks, and we can give a measure against one or probably two, but not to all of them. This is rather impossible, I would say. Yeah, so we are working in kind of active attacks. What is an active attack? So suppose that we have a network, social network, then we have to think about some things. First of all, what is called the adversary background knowledge of the any object. Of course, when you have a network, imagine a graph with several data. The adversary or the person who wants to do something wrong there needs to know something, some information. What he could know? Well, several things. Well, it should be some structural information about the network, of course. So one of the things that the adversary can do is that it can create or insert in this network some nodes that are controlled under the control of the adversary. Yeah, and with this person can establish some links between other nodes in the network. In this way, he can create a kind of fingerprints that after can be taken. I mean, imagine we have this data with every people. Then I am going to the hospital. I am describing the hospital. I'm saying that I'm sick with something. I'm staying there. I tell that I have this, and this 3 sicknesses. And for each of the sicknesses, they give me some treatment. Yeah, but I know that probably my neighbor is also going by the same problem. Yeah, so I know that only one of the problems. So I know that this. Then I know that I will be neighbor of my neighbor in the graph. That once the graph is public, then I know more or less who are my neighbors. So from my neighbors, I probably know that it's this one. And then I can get extra information from this person, okay? So this, once released the network, the adversary could take this fingerprint already introduced and then re-identify other elements of the network, yeah? So what is the privacy measure which we are taking? Well, this comes then to K anti-resolving sets, which is something related to resolving sets. What means that? We have a set of vertices in a graph, S, and then we say that for any vertex which is not in S, there are at least K minus 1 other vertices not in S, which are not identified through distances by S. And this K is the maximum possible. I mean that if I take a vertex, a set of vertices, for instance, this is my graph. This is my graph. I take a set of vertices and I will take one vertex here, and here are 5 more vertices that are the same. So I mean, all these vertices have the same distance to all the vertices in this set. Then probably there is another part here, and there are 4 vertices. They all have the same distance to here. And here there are 3, and so on and so on. Here 4, here many, and so on and so on and so on. In this way, I can make kind of partition of the graph. So here is my anti-resolving set, and here are all these vertices that are having the same distances to all the vertices in the graph. Indeed, they form an equivalence class, yeah, because all of them are related. When I get this partition, then this set S, which I have here, is a K anti-resolving set, yeah, for K equal to the minimum of the cardinalities of all this set, I could call PI, yeah, because this is the smallest possible, which is doing that. And it cannot be taken as a value smaller than K because there is one larger. I mean, if this is 3 anti-resolving set, it cannot be 2 anti-resolving set, because indeed all these sets will have at least cardinality 3. You know, this the reason that saying that K is the maximum possible. Yeah. And then the K metric anti-dimension is the minimum cardinality among all possible K anti-resolving sets. For instance, just a simple example. This set in blue form a 2 anti-resolving set because, for instance, for this vertex, there exists this other one. They both have the same distance to both of these blue vertices. For this, there exists this other one. And for the last one, there exists this other one. They all are having the same distance to all the vertices in the graph. And now, how to see this with respect to the privacy model? So we have active attacks, the privacy in a graph, and the attacker control a set of nodes in the graph. Yeah. And this set of nodes control the vertices if they can identify them in sense of distances. I mean, the background knowledge of the target in the graph is precisely the vector of distances. The attacker is able to compute the distances to all the vertices of the graph, and in this sense, it can have this vector of distances to it, yeah, to the set. However, well, this is what I was saying. The adversary, a background knowledge of the target, is the metric representation of the vertex with respect to the set of vertices. So, oops. We have a set of attacker nodes, and if this set is a K anti-resolving set, yeah, maybe it happens that the attacker node controls some set of vertices, and it is a K anti-resolving set. If it is the case, then the adversary cannot uniquely identify other nodes in the network with probability higher than 1 over K. Well, imagine that this person which wants to do something wrong, go there, puts the fingerprint, enters, and after it is published, he controls set of nodes, 3 nodes, 5, 10, yeah? But then when the graph is released, he can compute all the distances, and this is what he knows about the people there in this place. But if there are for each one at least K minus 1, mean that for every vertex there are at least K minus 1 like this one, then these people cannot identify anyone with probability higher than 1 over K. I mean, for each one there is at least K minus 1 like me. Yeah, so I am in a group in which I am not identified. I am there, but he doesn't know exactly who I am. Yeah. So in some sense, I need a K value which will be as large as possible. Yeah. Very small values of K, well, it's not a problem. It's a problem indeed. Indeed, if K is equal to 1, the probability is 1. So it means that the adversary can control at least one element of the graph. So with this, then is what we create this privacy measure, which we call KL anonymity. It means that we have a graph G. We say that this graph meets KL anonymity with respect to active attacks if K is the smallest positive integer, such that the K metric anti-dimension of this graph is lower than or equal to L. Yeah. So first of all, this value K is used as a privacy threshold, and while L is an upper bound on the expected number of attacker nodes in the network. I mean, this L I have to assume more or less what is it. However, this L in general can be estimated through statistical analysis. But you can imagine if you have a network in which you have 100 nodes, and in the 100 nodes you have 90 attackers, you are not doing anything there. We are almost done. It's impossible that the person which controls 90 attackers would know. It means that the attackers in a network are usually very small. If we have a network with 100, you should expect to have 1, 2 attackers, 3 at most. Otherwise, then it makes no sense to think about it. Yeah. So we have an example. This is a very simple one. Take, for instance, the complete graph. Yeah. And we know that in this network, it is hoped to have 3 attackers, for instance. So we need to find the smallest value K such that the K metric anti-dimension of this K12 is at most 3. And then if we take 3 vertices, yeah, we see that these 3 vertices form, well, there are 8 vertices outside, and then all of them are having the same distance to all the vertices in this set, because it's complete graph, of course. So the 9, well, the value that I'm looking for is 9 then, because the 9 metric anti-dimension of K12 is equal to 3, exactly. It is satisfied what I'm looking for. So this means that 9 is the minimum value for K, so that this is happening, and this means that this graph K12 meets 9,3 anonymity. It means that a node can be only identified with probability 1 over 9 under the assumption that we have 3 attackers. So if you have more than attackers, then the probability decreases. If you have less, then the probability increases. Yeah. Well, on the contrary, as I was telling you. So this is more or less how it works. Of course, complete graphs are the trivial case, I would say, because there are all connections, so it makes no sense too much. Yeah, just to put an example of how it works. Okay, in general, for every n larger than 0 and L and between 0 and n, the complete graphs meets k n minus L, comma L anonymity. Yeah. So as you can imagine, then studying this privacy measure and made it real and apply to something needs first study the k-metric antidimension of a graph. And this is things that I will try to speak a little here. So the k-metric antidimension, first, in theoretical point of view, combinatorial properties of it, and after some kind of application, probably. First, some interesting comments. Well, not for every graph of order n and every k smaller than n, there exists a k anti-resolving set in a graph, or you can imagine that this will not always exist. For instance, if we take a path and we consider k larger or equal than 3, there does not exist a k anti-resolving set in the graph. Of course, in order that you will have this property that all the vertices will have the same distance to all the vertices in the graph, the maximum that you can take for this k is the maximum degree. Yeah, because whenever you will take a vertex in the set, it has outside some neighbors and they all need to have the same distance. So you can have at most the maximum degree. Otherwise, no, it's not working. Then if we have a path, then k should be at most 2. Yeah. So we say that a graph G is k-metric antidimensional if k is the largest value such that the graph has a k anti-resolving set. Yeah. Well, with respect to this, there is one interesting detail here. If we have a graph G which is k prime antidimensional, then G has for sure k anti-resolving sets when k is 1, 2, and k prime, but not necessarily between 3 and k prime minus 1. This is because there is no monotonicity here. I mean, the k-metric antidimension is not related with the k plus 1 antidimension and not with the k minus 1. It could happen that we have one value for k, and for k plus 1, we will have another value smaller. We cannot increase or decrease. There is no monotonicity. Yeah, this is one big problem which we have working with this. And this is indeed one of the open problems which we are trying. When there exists a k anti-resolving set for some specific value. Yeah. Well, one very simple case, one very important case also is when G is one metric antidimensional. Yeah. It means that the largest anti-resolving set that I can find is when k is equal to 1. And if k is equal to 1, what is happening? Can you guess? Can you see? If k is equal to 1, it means that when we have one anti-resolving set, for every vertex outside of this set, there are 0, well, not for every, at least for one vertex, there are 0 vertices which are like him. Yeah. K equal to 1, there are k minus 1, 1 minus 1, 0. So at least for one vertex, which is not satisfying the property, there are 0 vertices like it. So this is really problematic because this means that this vertex can be identified easily. So those vertices, those graphs, which are one metric antidimensional, are really not good for being used as a metric, as a social network to be published. And there are a lot of them. One very simple example, I don't know if I have it there. No. One very simple example, which one is path of even order. If you consider a path of even order, no matter which set you will take, it will be only at most a one anti-resolving set. You consider one vertex. For this vertex, there exists this, yeah, but this is having no one. If I consider some in the corner, the same. If I consider two vertices, it is even worse. So it is not possible to find one k anti-resolving sets for k larger than 1. For odd cases, no problem, because I take just the center and this is the 2 anti-resolving set. Yeah. So paths are 2 metric antidimensional if they are of odd order, and if they are even, they are only one antidimensional, metric antidimensional. Well, the problem clearly, when you will take one graph which is one metric antidimensional, you can take whatever set. All of them will be one anti-resolving set. So the one metric antidimension is indeed one, yeah, the smallest possible. So the problem in general of computing the k-metric antidimension becomes interesting when k is larger or equal than 2, yeah, because when k is 1, you will always get the same. However, the one metric antidimensional graphs are interesting, as they say. They do not meet any privacy feature. Yeah, they are not private at all. So in this sense, it will be interesting to know which are those graphs, which are one metric antidimensional. And what's that last comment? K anti-resolving sets somehow arise from K resolving sets. Well, K resolving sets is a generalization of resolving sets. Probably you have seen something like that. So first thing is finding for instance, the K-metric antidimension of some graph. When did I begin? At 11? 11 or 11 and something? 11:30? Okay, so 11:30? How much time I still have? I don't know. 24 minutes. Okay. Well, some kind of examples and exercises I was saying that. Of course, the first thing I was saying that if we have a connected K-metric antidimensional graph of maximum degree delta, then the K should be at most K. And path and cycles I was already speaking about. The even are one metric antidimensional, the odd ones are two metric antidimensional, and the K-metric that the one metric antidimension is one, I can take only one. And in the case of cycle, both of them are equal to one. So a dim sub one of a path P to n plus one is equal one and is equal to a dim sub two of P n to P n plus one. Yeah, just take the vertex in the center for the case K equal 2, and for the case equal to 1, take another vertex, not the center. Because if I take the center, it's not the one anti-resolving set, but the two anti-resolving set. But any other vertex will be one anti-resolving set. Now, what happens if I consider cycles? Well, in the case of cycles, first of all, they are two metric antidimensional. Yeah, they cannot be more than 2 because they are of degree 2. So we can compute the one metric antidimension and the two metric antidimension. For the case of one metric antidimension, it depends on if the cycle is even or odd. Because if the cycle is even, I just take one vertex and there is one unique diametral. So this is doing that this vertex is the unique that is having the same distance to it. So in this case, the one metric antidimension of this cycle, even cycle, is 1. But if the cycle is odd, then we have some problem, because whenever we'll take one vertex only, then there are two vertices always at the same distance to it, even at diameter. So the two metric antidimension of the one metric antidimension of one cycle cannot be 1, but should be 2. Then whenever you take 2, then you are done. Two adjacent, for instance. And for the two metric antidimension, yeah, of a cycle, we need to take two vertices, which will be diametral in the case they are even. Yeah. If it is even, I just take, well, this is not even, no? Well, yeah, okay. In the case I just take these two vertices, and for every vertex there exists this, yeah, that they are at the same distance to all of them. So the two metric antidimension in the case of even cycle is 2. But in the case two metric antidimension of a cycle, when cycle is odd, then I just need to take one vertex. Sorry? Only one, because then for everyone there exists two vertices. So if I remove this one here, you see, this one has two diametral and always two vertices at distance, the same distance. So they are, this is a two anti-resolving set. Now, when we consider complete bipartite graphs, then this complete bipartite graph, when, well, we will take K RT and R larger or equal than T, is R metric antidimensional. It is the same, like it coincides with the maximum degree. Maximum degree of the complete bipartite graph is, in this case, is 2, 3, for instance. Yeah. The maximum degree is 3. Yeah. So then it is 3 metric antidimensional. And then I can compute 1 antidimension, 2 antidimension, 3 antidimension, and so on till arrive to the maximum of the values. Yeah. And this is, well, a little more problematic. We can see there are several cases between one interval and other ones. For instance, between between 1 and t, the smaller of the values, not including 1, not including t, then this value t minus k. Well, I think that 1 is included here. When k is equal to t, then we have these possibilities. If they are equal, it is r, or if they are larger, then it is just 1. Or when k is between t and r, then we have this formula. So there are several situations that could happen. This is more, little more elaborated, but also not that problematic to see. And now, for instance, the case of trees. Well, the case of trees becomes really problematic also, unless the tree is, of course, a path or a star, for instance. Yeah. If you consider any tree, yeah, something, whatever shape I will take, there are no, I know some things, for instance, that if I consider k equal probably 3, for instance, then for this vertex there exists 2, and then I could say, okay, this is a 3 anterior solving set, and so on and so on. I can compute some things. But probably there are some structures which are giving me the same thing, and even that they will be in one part or in the other. So somehow I cannot control exactly what is happening. So for the case of trees, the problem is really challenging. I don't know how to exactly will work, because you can find several situations. Probably for some value k, you will get something easier, but when you increase or decrease this k, then it can change dramatically. So I don't know exactly what it was. It is an open problem, so you can consider it as if you are interested. So these are some basic results. And until now, there are few things that have been done. For instance, there are some algorithms that are kind of, how to tell, statistic, randomly are working for random graphs. Other thing that we have made is we have taken some real life social graphs. Yeah, some we have taken that you can find it in the web, in internet, some information about some databases in which you can get the information about the social networks. And then with this, with our privacy measure, we were computing the value for each of the network and seeing how much secure they are. Indeed, they are almost all of them, they are not secure. So it's not something surprising, I would say. So what it says that it is not surprising that all social networks are not exactly secure. Then we have studied some other properties of the k-NT dimension. It is proved that it is NP complete. Well, there are some NP completeness of some related optimization problem related. Yeah, it is interesting because when we were working on that things, we presented our first article in which we studied all the things related to the social measures and give a few properties of the anti-dimension. And after that, we tried to continue working on this. And some people from China also were working in the same time like us. They began to study and they were able to prove that this NP complete or NP hard, I would say, to prove that to compute the k-metric anti-dimension. But at the same time, we were also doing the same and we obtained the similar result with different reductions, but we obtained the same. And we did also some privacy evaluations of other real networks, which are in connection with the privacy measure. So this was also something that we made. Now, other thing that we, after the decade time was that of finding those graphs which are one metric anti-dimensional. I mean, since they are really problematic, we should be aware of them. Then we decide, okay, we will think how it is with this. And we began with the case of trees. Well, first, some properties. First, every set of the graph is a one anti-resolving set when it is one metric anti-dimensional. And of course, there is not any k anti-resolving set for every k larger or equal than 2. And then whenever you will take one set, which is one anti-resolving set, even that will be of cardinality 1, it is able to identify at least some vertices in the graph. Yeah. Well, this is what I was saying. For every vertex, there exists at least 0 other vertices. Well, here is not for every. It should be, there exists one vertex V not in there, so that, blah, 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 all the same. And they have no privacy. And then we were trying to work on the one metric anti-dimensional trees. First of all, which are those graphs? Well, first is say that we need to know the concept of eccentricity and branches. I mean, if we have a tree and we take this vertex here, the branch is this one. Yeah, all the vertices are hanging from it. So consider, oh, here is an example. An example of a branch. We have a vertex in a tree, and the branch is all the vertices with all the descendants of this vertex in one direction. So the first property that was interesting for us that helped much, it was that when we get a k anti-resolving set in a tree, and this k is larger or equal than 2, then this set induces a tree also. I mean, that is connected. The set, which is a k anti-resolving set, is connected. And how it goes this? Imagine that we have a k anti-resolving set, which is like that, for instance. Yeah, it has part here, and this disconnected. Then we clearly have some path which is joining some vertex here and with some vertex here, and this path is unique, clearly. Yeah? So if you see for these vertices, and you look for the metric representation of this vertex with respect to this set, you will see that it is unique. There is no one like him at this point, yeah? Because it has distance 1 to this vertex, and there is no more vertex which is having distance 1 to this vertex. Also here, or, well, here, for instance, probably not. But this one, it is also unique. So it is not a k anti-resolving set for any k larger or equal than 2. It can be only one anti-resolving set. So this is a contradiction, and we get that our k anti-resolving set must be connected. So first, we also needing something called equivalent branches at the vertex. So, for instance, consider this vertex. I added some leaf here to be clear, and then we'll see that this branch has a height, I would say, from x till the end. 1, 2, 3, 4. Yeah. So the eccentricity of the vertex x in this branch is 4, and these all three also have the same property. Yeah. The eccentricity of the vertex x in this tree is also 4. They have the same eccentricity in both trees. Then we say that these two branches are equivalent. Yeah. And then for every vertex x, we define this parameter chi. Yeah. Sub t of x, which means that the number of equivalent branches of this vertex. Yeah. For instance, in this tree, this has chi of this value is equal to, because there are 2 equivalent branches. But if you see, for instance, this one, it has no equivalent branches because the 1, 2, 3, and I should consider also this other one. Yeah, going from the other direction, but this is much larger. And this one has 2. Yeah, because here are. This is 2, but this is longer, and this other one is longer. And for the other ones, the same. This is here. You see this vertex has 1 only because it is 1 and 2, and this one has only 1 because all the branches are not equivalent. So we were needing to define this parameter, and once we have that, for instance, here in this case, there are no equivalent branches at any point. It means that when we have 2 equivalent branches at some vertex x, there exists a k anti-resolving set with k larger or equal than 2. For instance, consider here this tree here. If I now remove all this part, yeah, and I leave outside of the set only this part here, the two equivalent branches without the vertex X, you will see that for any vertex here outside in this part, there is one more which having the same distance to all the other ones. Yeah, for this exists this. They have both the same distance. For this, there exists these two. For this, there exists this, and for this, there exists this. They are always at least two vertices having the same cardinality, the same distance to all the other vertices in the graph. And then this means that this is a two anti-resolving set. Yeah. So then this cannot happen. And this precisely gives the idea. Well, here it was. If I consider this vertex, you will see that, well, even this also I can leave it out. These two branches here are doing that. This in blue is a K anti-resolving set. So the property is that for any vertex, we should have this property. Doesn't matter which one is. So a 3T is one metric antidimensional if and only if the number of equivalent branches is one for every vertex of the tree. So I see it's a tree which is a lot not symmetric. You see, for instance, well, I think it's here. No. You see, all the branches are of different height. This is a smaller, this smaller, this smaller, this smaller, that this here all. And if we comparing this, also this is smaller. So you will always find someone which is far away. Yeah. And with this, then this is the characterization of the trees, which are one metric antidimensional. And the most interesting case is that it is possible to implement this one in an algorithm, which is saying in polynomial way, if a given tree is one metric antidimensional or not. Yeah. So this is the algorithm. So the next step then was, what happened if I consider now other graphs? And then we pass to the case of unicyclic graphs, just adding one edge. Well, when we add one edge, the thing comes more or less in the same idea, but then we get a characterization which is bigger, longer, with several more conditions. Yeah, but there still is characterization which can be checked in polynomial time. So for any unicyclic graph, we can make it also. But after a unicyclic, we didn't continue. Yeah, well, polynomial algorithms these are now. Yeah, so one open problem now that I would like to explore at some point is to continue finding graphs which are one metric antidimensional for some families or for all the graphs. If we are able to, whatever graph give, okay, perfect. But I am hopeless that we will be able to give in general. So mainly, I think that we will work on some classes of graph, and then among these classes, we'll say these are one metric antidimensional. There should be some graphs which are very anti-symmetric. So as soon as there are some symmetries, then you are having problems. So there are some other results about one metric antidimensional graphs due to these people, Mao, Yu, and Chuan. And well, one interesting open question is precisely to find all one metric antidimensional graphs. And these are some references that you can use for that things. As you see, this is the first article with a measure. Here are some statics. This is the article containing things about one metric antidimensional things. This is the article which people from China made about the complexity of the problem. And here we have two articles more for the analyzing and evaluating the privacy measure for social graphs. And here is the other article which we had on the computational complexity of the problem. You should, for instance, notice that this article and this last one are published in very high top journals. So information sciences is one of the highest journal in computer science in the world area, and they are very restrictive. So it is not that it's published there. So these topics are well collocated always if we are able to get some contributions there. Yeah, and that's it.
Yes, question, please.
Did you implement this algorithm?
This algorithm is for checking when a graph is one metric, a tree is one metric antidimensional, and there exists one similar one for unicyclic, but we didn't implement it then. I mean, we didn't do any implementation that will check over some trees or some unicyclic graph how it works. We didn't implement it, only develop the algorithm, and that's it. We didn't implement it. Yes.
If considered to be aging dimension or not, if we consider vertex takes outside of the sphere, and then another vertex takes, then the distance need to be equal to other than.
Well, for any vertex, if we consider a K anti-resolving set, for any vertex outside, there are K minus one other vertex that they have the same distance to all the vertices of the graph of the set, but not the same distance. Mean that they could have all them distance 1 to one vertex, and to the other one they could have distance 3, and to the other one could have other distance. So
let's say X Q1 is X1, X2, X3. So the R what is the same distance simply to be equal from the X1 and from X2 and from X2.
yeah.
R is not if one the distance between X1 is 1, X2 is 2, and X3 is 3.
Yes.
And the other the distance between 3 is 1, X2 and X1 is 3. Then they will be in the same class.
No, they are different classes because this is a vector. I mean, they need to have the same vector of distances. This probably what you say is trying to understand as a multiset. Maybe this is something other, but we are working on this already. So this is our next step. Yesterday, before I was speaking about multiset dimension, and we are now working on the multiset version of anti-dimension. Yes, we have some advanced article will appear in probably 3 months. Yes. This is even harder, but it is nice. Sorry?
Yeah, you mentioned lecture. Is it related to holding us in a graph? Because sometimes in nothing you graph with some holding us also. So is it the same as the attackers in the mention?
No, I don't think so. I don't think so. The faulty nodes is something other, probably. No, I don't think something different, I guess.